In a previous video, we examined phase portraits for linear autonomous 2x2 systems of ordinary differential equations, systems of this form. In this video, we'll look at nonlinear systems, and we're going to look particularly at two features of them, separatrices and basins of attraction. For linear systems, the resulting graphs were determined by the eigenvalues of the coefficient matrix A. Those graphs manifested a great deal of symmetry, and their nature was completely predictable from the eigenvalues and eigenvectors of A. Now, in this video, we're going to consider nonlinear systems. So here's a nonlinear system. F and G are not presumed to be linear functions. Now, under relatively mild conditions on F and G, we still have a phase portrait. That is, a family of non-intersecting curves in the plane whose coordinate functions, x and y, x and t, y of t, parameterize the solution curves of the system. While for nonlinear systems, the nature of the solution curves is no longer predictable a priori, the phase portraits still manifest a remarkable degree of regularity. Two of those regular features are separatrices and basins of attraction. So what are these? Well, we described in the first video on autonomous linear systems what the critical points of a system are. The critical points are namely the common zeros of F and G. If x0, y0 is such a point, then if you define the parametric curves thus, so x of t is equal to x0 for all t, y of t is equal to y0 for all t, then of course you just have a point, the curve is a point, and that's a stationary solution of the system, or what we often call an equilibrium point. And then we can make the following definitions. A separatrix is a solution curve running from a critical point to another critical point or out to infinity, such that the behavior of the solution curves on one side of the separatrix are all the same, and similarly on the other side of the separatrix, the behaviors are all the same, but the two behaviors are distinct from each other. That definition may seem a little mysterious. It will be clarified in a minute when we look at a particular set of examples. Second is a region called a basin of attraction. So a basin of attraction for a critical point x0 is a region in which every solution curve that starts at a point in the region tends to x0 as t tends to infinity. So we're now going to give three examples. The first two examples correspond to nonlinear systems which are not particularly related to any specific phenomenon studied in the course, but they're very nice examples. And the third comes from a population model that will be addressed in the third video on autonomous systems. It's also addressed in the MATLAB presentation on nonlinear systems, and you might also compare its phase portrait, which we'll draw in a moment, to the cover of the differential equations book. And now it says here, go to the next page for the three examples. Here they are. So those are clearly nonlinear systems. The expressions in x and y on the right-hand side are not linear, not even close. And in each of the cases, you can compute what the critical points are. It's a little bit of an algebra exercise to see what the common zeros, for example, of these two guys here. Excuse me. Okay, now let's take to a more concrete examination of these three systems, and of course we will use MATLAB. Okay, it's time to turn MATLAB loose on these three examples. First, let's clear everything. And now look at the first example, same as the first example on the preceding page, nonlinear system. And the phase portrait for this and the other two examples will be drawn by, of course, invoking the numerical solver, MATLAB's numerical solver, which is ODE 45. The resulting graphs may not reveal, they don't necessarily reveal the direction of motion on the solution curves. So we shall first draw the vector field for the system and then combine it with the phase portrait. So the vector field will enable us to determine the direction of the solution curves. So here's our first computation. This is the first example using the code from chapter 15 of the differential equation with MATLAB book. we first set up a grid of points with x running from -4 to 4, y similarly, and a step size of half, excuse me. There's the differential equation. This is the standard normalizing command, which guarantees that all the vectors will be of the same length. Quiver plots the vector field, and I named it basically vector field plot 1 because I'm going to use it. Let's run this. And there's our vector field. There are 4 equilibrium points. There's one here. Looks like a spiral point. One there. A saddle. And these two are nodes. This one unstable. Curves are going away. This one is asymptotically stable. The curves are all coming in. Okay. Now let's go on to the phase portrait. So here's the command, the code this time from chapter 14 of the differential equations with MATLAB book. New figure, we incorporate the system into this anonymous function f. We set up a loop, again with the x and y axes both running from -4 to 4 with step size of half. Use OD 45 to plot the solution, and let's see what we get. Takes a little bit of time since there's some numerical computations to be done, and there's the phase portrait. Next, let's combine the phase portrait with the vector field. So that will be this command here. If I run it and bring the graph back up, there it is. There's both the vector field and the phase portrait drawn together. And you can see the solution curves, some of them going like this, some going like that. Some going around, coming into here, and some apparently spiraling around into here. So let's take a look. The graph reveals, together with a little algebra, using the method of almost linear analysis, which you've learned, it enables you to conclude that the 4 equilibrium points and their type and stability are as follows. So let's again bring the graph up. 0, 0 is right here. That's the saddle point. 0, 1 is the asymptotically stable spiral point. 3 minus 2 is over here, the unstable node. And minus 2, 2 is over there, the asymptotically stable node. And now let's draw the separatrices. So I'll let you read the code. It's explained in the MATLAB book. But you'll see there are going to be 2 separatrices. Let's run this and bring the graph back up, and there are the separatrices. They both run from the unstable node to the unstable saddle point. One goes along this solution curve and the other goes along this one, and in between the two is a basin of attraction for the asymptotically stable spiral point. And outside this region, anywhere out here, is actually a basin of attraction for this asymptotically stable node. Every solution curve outside this basin actually comes around into here. They all do that. I mean, even if you go way out here, eventually it comes around and crashes into that point. So that's the words here. Let's bring it up again. The region between the red and black separatrices is a basin of attraction for the point 0, 1, this point. The region outside the region encased by the red and black separatrices, that's out here, is a basin of attraction for this asymptotically stable node. And aside from the separatrices, these 2 curves, there are only 2 other curves unaccounted for. This curve here and this curve here. They both go out to infinity. So as I said, aside from the separatrices and the 2 exceptional curves on the x-axis, every solution curve converges to one of the 2 aforementioned equilibrium points. Now for the second example, we'll go through this a little bit more quickly. There's our nonlinear system, and vector field for that system looks as follows. So what do we got here? We got, looks like a spiral point here, and maybe a saddle point here, and perhaps an asymptotically stable node over here. And next, let's draw the phase portrait. And yep, there's a saddle point, and this looks like a spiral point, and here's a node. Curves coming around here, some curves going in there, curves coming in like this. So, NX combine the two, and bring it up again. So you certainly can see what's going on. The curves going around like that, some of them coming here, some of them going in here. Obviously the saddle point is going to be involved in a separatrix along here. Below it the curves are going to go like that. Above it they're going to spiral in. Let's take a look now at these words and again bring up the graph. Same words, again, use the method of almost linear analysis. The point 0, 0, that's here, is an asymptotically stable node. The point 1 minus 1, so that's here, is a saddle, and the point 1 minus 2 is an asymptotically stable spiral point. So let's draw the separatrices. Again, they're going to be 2. And run it, bring up the picture, and there's our separatrices. So this time they run between this saddle point and infinity. So there's one separatrix going out to infinity. Here's the other one coming around, and in between here we have a basin of attraction for the spiral point at 1 minus 2, and outside that region we have a basin of attraction for this asymptotically stable node at 0, 0. So that's what these words say. The narrow region between the red and black separatrices is a basin of attraction for the equilibrium point at 1 minus 2, this asymptotically stable spiral point. The remainder of the plane is actually a basin of attraction for the equilibrium point at 0, 0. Every solution curve except the two separatrices and the saddle point is tending toward one of the two aforementioned asymptotically stable equilibrium points. Again, though, what about here? Actually, even these work, right? These are coming in. Right? So every curve. There aren't the two exceptional curves like you had in the preceding case. So there's a nice phase portrait with the vector field and the separatrices which bound the basins of attraction. And finally, our third example. Here's the nonlinear system. This is actually a predator-prey model in the case that the prey satisfies a logistic with threshold assumption. So we'll do it the same as we did the previous two. We'll first draw the vector field. Here we go. So there's the vector field, and I only drew it in the first quadrant. You can see what looks like an asymptotically stable spiral point here, but there's actually three saddle points, well, two saddle points. There's one here, right, the arrow's here, arrow's here. Another one here, arrow's coming in, arrow's coming in. And there's a third critical point here at the origin. All these arrows seem to be coming in here. So it looks like it might be an asymptotically stable node. These two spirals, saddles, and this guy is spiral. Okay, let's draw the phase portrait. Yep, that's what happens. Right, here's your saddles here and here. Here's your spiral point, and this is an asymptotically stable node. In case that's not completely evident, you might think the curves are running out. Let's combine with the vector field. Bring it back up, and you see all the arrows are coming in like that. Okay, so the graph reveals, same words as before. You can use the method of almost linear analysis to confirm that the origin is an asymptotically stable node. 1, 0 and 3, 0 are saddle points, and 2, 1 is an asymptotically stable spiral point. Okay. So now, in this case, it turns out there's one separatrix, And I'm going to draw it. There it is. There's the one separatrix. Below it, solution curves all come and go spiraling around that point. Above it, the solution curves all come and crash into the origin. So under the red curve, under the separatrix curve, we have a basin of attraction for the asymptotically stable spiral point 2, 1. And above the separatrix, we have a basin of attraction for the origin 0, 0. I had one other question. What happens if you start out on the axis? So it should be obvious. I only did this in the first quadrant. What if you start out on the axis? Well, if you start on this axis, you crash into the origin. Here, it depends. Right? If you start out here, into the origin. But if you start out here, you go out to infinity. And in here, you come to this point. No, actually, you converge to the point 3, 0, no matter where you start out here. Okay, that concludes our discussion of separatrices and basins of attraction for nonlinear systems. There are many more examples to be found in the notes and in other places online if you care to search.